Hey you guys, this is section 2.2, which is about proving that lines are parallel. So in this section, you're going to be tasked with using angle relationships to prove that lines are parallel. Essentially in 2.1, you all learned three theorems in one postulate about if two lines were parallel, what relationships their angles had. And now we're going to use what we learned in section 1.5 about the converse, which was if we flip around our conditional statement and we put the then in front of the if, like we move them around. And that's what you're going to be doing in this section, is now given the angle relationships, we're going to prove the lines are parallel. So in this case, we won't actually know that they're parallel, and we're going to use what we can see about relationships to then prove that lines must be parallel. So pause and write down the four converses of the theorems and postulate that we learned. It's essentially the exact same thing, but stating now that if you know the angle relationship, then the line must be parallel. Pause and jot those down. Now we're going to try example 1. We're going to move straight to example 2. And example 2 asks us to write a flow proof. I've marked out the word flow. We're going to stick with our 2-column proof. Write a proof for theorem 2-6, the converse of the same side interior angles postulate. So what I've put for us here is in black ink, I've put the postulate, which is 2.6. If the measure of angle 1 and the measure of angle 2 equal 180 degrees, then the lines must be parallel. And that's what that postulate tells us. We're going to actually be tasked with proving that is true right now. So pause and sketch out into the side a little figure for us to reference. And now since we're trying to prove this, our given is going to be that the measure of angle 1 and the measure of angle 2 equals 180 degrees, because that is the first part of our statement. And what we are actually going to try to prove is that we know the lines must be parallel. So let's get our 2 columns going, and I've already written our given as our number 1, that the measure of angle 1 plus the measure of angle 2 equals 180 degrees, and that is given to us. So now let's look at this figure, and what else can we notice about this figure? What other angles do you notice also equal 180 degrees? 1 and 3. So that's going to be where we logically go next, is to build off of what we can see. So my statement number 2 is going to be that the measure of angle 1 plus the measure of angle 3 also equals 180 degrees. And we know that because they are supplementary angles. They are created on the same line. Okay, so let's use that we know that 1 plus 2 equals 180 and 1 plus 3 equals 180. So let's do some substitution and set those equal to each other. That means that the measure of angle 1 plus the measure of angle 2 must equal the measure of angle 1 plus the measure of angle 3, and that is by substitution. Again, don't abbreviate it sub unless there's no subtraction, because that gets confusing. But let's think. We're trying to prove that the lines are parallel. Well, let's just keep going with what we see here, because I see that there's a measure of angle 1 on both sides, so I'm actually going to subtract that, and those will undo each other, and I'll have that the measure of angle 2 equals the measure of angle 3 by subtraction. See how I couldn't use sub on both parts because it would have been confusing? I could have abbreviated sub then as subtraction because I've already spelled out substitution, but I can't use sub on both parts. Now, what do we naturally know? That if the measures are equal, what do we know about the angles? We know that if the measures are equal to each other, then the angles are congruent. So that means that angle 2 is congruent to angle 3 by the definition of congruent angles. And you're probably wondering, Miss Meyer, where are you going with this? But if we know that angle 2 is congruent to angle 3, Look at the postulates and the theorems that you just wrote down, the converses, and is there one of them that states if corresponding angles are congruent, then the lines are parallel? Yes, there absolutely is. The corresponding angles theorem, the converse of that, so one of the ones you just wrote down, tells us that if corresponding angles are congruent, then the lines must be parallel. And we just proved that corresponding angles were congruent. So the lines must be parallel. So L must be parallel to M. And our reason here is by the converse. Why is my text so big? 1 second. That's why. The converse of the corresponding angles theorem. So notice how we just use one of the theorems to prove that a different one was true. We just use the converse of the corresponding angles theorem to prove the same side interior angles postulate. So you can use anything you know in geometry to prove things. We just couldn't say that the two lines were parallel because they were same side interior angles. We didn't know that for sure. We used a different theorem to prove this postulate, because we know that if these angles are congruent, then these lines must be parallel because of this theorem, which you just took notes on here. Now let's move on to our next example. And the example comes with a diagram that for some reason is not in your book. I'm always very sorry about that. It is this beautiful traffic figure that if you want to pause and out to the side, I've kind of sketched just some lines for you where we have the horizontal transit lane, we have these diagonal lines. We don't know that they're parallel, but we are given the measure of two of the angles are 53 degrees, and we are labeled angle 1 and angle 2. We don't know anything more than that, but let's sketch it. And it tells us that the edges of a new sidewalk must be parallel in order to meet accessibility requirements. Concrete is poured between straight strings. How does an inspector know that the edges of the sidewalk are parallel? So right now we do not know that they're parallel, and we want to prove that. And one way can be the inspector can first measure the angles of the corners of the sidewalk, which is what we have here in our diagram, that we have this is 53 degrees and this is 53 degrees. And now if you can think about this as the horizontal line being our transversal, then those two 53 degrees are alternate exterior angles. And the converse of the alternate exterior angles theorem tells us that if alternate exterior angles are congruent, which here they are, exterior being outside the parallel lines and alternate being on opposite sides of the transversal, they're congruent. So that proves that the sidewalks must be parallel. So let's take it one step further and do the example in your workbook. What is the measure of angle 1? So if we know that this is 53 degrees, can we find the measure of angle 1? Yes, we totally can. The measure of angle 1 plus 53 degrees equals 180 degrees because they lie on the same line. So if we subtract 53, the measure of angle 1 must be 127 degrees. Okay, we've answered that question. What should the measure of angle 2 be in order to guarantee that the sidewalk is parallel to the main street? So if we want to know that the sidewalk here is parallel to the main street, what does the measure of angle 1 and angle 2 have to add up to be then? They have to add up to be 180 degrees. Because for those things to be parallel, those angles must add to be 180 degrees. So we know that the measure of angle 1 plus the measure of angle 2 has to equal 180 degrees for those lines to be parallel. And we know the measure of angle 1 is 127 degrees. We don't know the measure of angle 2 just yet, but we can solve for it. The measure of angle 2 must be 53 degrees. We also could have known that from alternate interior angles. We don't know that it is, but that's what it would need to be in order for those lines to be parallel. And then in our last example, there are two theorems that we are going to discuss, and we don't necessarily need to write them down, but we do need to go over them. And it simply states that if two lines are parallel to the same line, then they're parallel to each other. AKA, if this first line is parallel to this third line, and this second line is parallel to the third line, then the first line must also be parallel to the third line. They are all parallel. Beautiful. Same thing with right angles. If two lines in the same plane are perpendicular to the same line, then they are parallel to each other. AKA, if this is perpendicular to A, C is perpendicular to A, and C is perpendicular to B, then A and B must be parallel. We're going to use that knowledge to do example 4, which also has a figure in it that is not in your book. But it's a kind of picture of a gate that I've sketched out, and I've put all the information that we're given in it. So we are given 3 horizontal lines, A, B, and C. Check. We're given 2 vertical lines, V and W. We are given these 2 right angles between A and V and W and A. We're given an angle 1, an angle 2, and angle 3, and we're told the measure of this angle. So I have written all that down in this figure for you if you want to just pause and draw that and use that instead of referencing this picture of a gate. And the initial example that's in our book, that's not in your workbook, says when building a gate, how does Bailey know that the vertical boards V and W are parallel? And from Theorem 2-9 that we just learned, since A and V are perpendicular and form this right angle, and W and A are also perpendicular and form that right angle, they must be parallel. So that theorem tells us that they are parallel. Check her gates. The 2 vertical boards are parallel. That's great. And now we can answer some of the questions that are in our workbook. I'm going to go down to this question in our workbook. Bailey needs board C to be parallel to board A. What should the angle what should angle 2 measure? So if we want, and I'm going to zoom out so we can see our figure, if we want C to be parallel to A, then the measure of angle 2 must be 90 degrees. So if we want C parallel to A, then the measure of angle 2 must be 90 degrees. Because we have to have that 90-degree angle here. And if this is perpendicular and this is perpendicular, then these 2 lines will be parallel. Because 2 lines perpendicular to the same line, aka C and A are both perpendicular to this vertical line V, they must be parallel to each other. And lastly, a question we can think about, is B parallel to C? So we've got horizontal line B. We want to know, is it parallel to horizontal line C? And let's look at the things that we know and are given. We again don't actually know the measure of angle 2. We're just saying that if we want them to be parallel, it must equal 90. We don't actually know anything about it. We don't know anything about angle 1 or angle 3. So from the information that we're given, can we say anything for sure about B being parallel to C? Is there any information we have that we can prove that this horizontal line B is parallel to our horizontal line C? We don't know if there are right angles here, like we don't know that for sure. That would be really helpful information. We have this transversal, and if they were two parallel lines, then we could know things about their angle measures, but we don't know enough angle measures right now. So this is a perfect example of sometimes things can't be for sure. So if is B parallel to C explained, we don't know. No, we can't say for sure whether it is. We do not know. There is just not enough information for us to be certain. So we can just say not enough info. It might be, but just solely based on the information we're given, there is not enough information to prove that B is parallel to C. We can speculate and we can look at the figure and we can assume that it probably is, but we also can't base facts on our assumption, and we don't have enough facts to prove that B is parallel to C. And that's going to happen sometimes, you guys. So make sure anytime you're saying something is certain, you have the facts to back it up.